All right, guys, we are going to move into Chapter 5. Chapter 5 deals all about probability. Probability is one of the most challenging chapters that we're going to see in the course. Today, our focus is really going to be about simulation-based probability, and the notes won't be that long, and we'll do a lot of examples in class. So, chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. This is the idea that if you flip a coin, say, 10 times, it wouldn't be that unlikely that you would get 7 out of 10 to be heads, okay, or 70%. Okay, because in the short run, probability can be unpredictable. However, if we flip a coin 7 or 1,000 times, it would be highly unlikely to achieve 700 heads or 70% heads. So in the long run, things will balance out. But in the short run, you could have unpredictable outcomes. This happens all the time, say, like at a casino. People are gambling, okay? And they think, oh, I lost 4 hands in a row. I'm due for a win, something like that. In the short run, probability is unpredictable. In the long run, it'll balance out, but in the short run, it's not. So that idea or that concept is referred to as the law of large numbers. So the law of large numbers says that if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. And that single value that it's approaching is the theoretical probability. So if you take a look at this chart that's shown here, this is showing the proportion of times that you get heads when you're flipping a coin. So if we look at this chart, you can see that as you do more and more tosses, look at the one on the left, you can see that there's a lot of variability. But if you look on the right, as we increase to 500 tosses, look how it hovers right about that 50% marker. Okay? Why? Because as you do more repetitions and more trials, it's going to approach that single value, which is the true theoretical probability. So what is probability, okay? If I ask you to define probability, a lot of people actually have difficulty understanding exactly what probability is. I know, okay, I say you flip a coin, it's 50-50 chance of getting heads. But what does that mean, actually? So the probability of any outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. That is what probability represents. It means if you do 1,000,000 times flipping a coin, 50% of the time you should get heads. That's what probability means, okay? It represents the proportion or the percentage of times that outcome would occur in a very long series of repetitions. We'll go through the example down here in class. Let's continue. So, again, the idea of probability seems straightforward. However, there are several myths about chance behavior that we must address. First one, which I kind of talked about, the myth of short-run regularity. The idea of probability is that randomness is predictable in the long run. Okay, and that's key. Our intuition tries to tell us random phenomena should also be predictable in the short run. However, probability does not allow us to make short-run predictions. Again, like I talked about, this is the idea, like say in a casino. You're playing the game of roulette, right, where the ball could land in red or black. And in theory, it should be a 50-50, red, 50% chance of black. So you look at a board in a roulette and on a casino, they'll show you what happened the last, say, 20 trials. And what people do is they say, oh, it's been red, 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 red. It must be black on the next one. We're due for a black. You're trying to make a short-run prediction using probability, but that's not going to happen. In the long run, it'll even out, and we'll get about 50% red and 50% black, but I can't use that probability knowledge to make a prediction about the short run. Next thing, the myth of the law of averages. The probability tells us random behavior evens out in the long run. However, future outcomes are not affected by past behavior. That is, that past outcomes do not influence the likelihood of individual outcomes, and that's key, occurring in the future. And again, this goes to that same concept that I was just talking about. Because our past outcome does not influence future outcomes or individual outcomes, the events are independent. So, one thing that's a little bit challenging that we can use to estimate probability is what's referred to as a simulation. Simulations imitate chance behavior. So the imitation of chance behavior, based on a model that accurately reflects the situation, is called a simulation. When you're performing a simulation, you're going to see these things that we saw earlier in the year. We want to think once again in a state, plan, do, and conclude kind of sequence. So first thing, state, ask a question of interest. About some chance process. Plan, describe how to use a chance device to imitate one repetition of the process. When you're doing that, make sure you tell what you will record at the end of each repetition. Then actually do it. Perform any repetitions of the simulation and conclude, use the results of your simulation to answer the question of interest. So a simulation is a way that we can estimate what the actual probability of some event occurring. We use simulations because sometimes it's really difficult to theoretically find that probability. If you think back to the beginning of the year, when we did that smelling Parkinson's example, that was an example of using a simulation to estimate the probability that she would get all 12 correct, okay? And again, we use these because a lot of times it's difficult to theoretically find that probability. When you're running a simulation, you can use physical devices such as dice, cards, things like that. You can use random number generators. You could use table D, your table of random digits. All of those things can be used to perform simulations. You can do names in a hat, numbers in a hat, things like that. So what is the purpose of a simulation? Again, like I said, to estimate probabilities that are difficult to calculate theoretically. So in essence, we're really finding an experimental probability. Okay? What are the 4 steps? We saw that above, which we described. That's our state, plan, do, and conclude. In simple terms, state the question that you're trying to answer. Plan, choose the chance device, such as cards, numbers, a dice that you're going to use, actually perform that simulation out, and then make a conclusion in context. Do you need the 4 steps every time? No, you don't, okay? Just make sure that you're consistent in what you're doing. Just be consistent, specific, and use context. What are some common errors when using a table of random digits? We saw a table of random digits in the last chapter, okay? Remember, when you're using a table of random digits, the labels must be the same length. And always, when you're doing this, specify whether repeats are allowed or not. We're going to do a lot of probability-based modeling in class with simulations. You'll see it's a little bit time-consuming and could be a little bit tricky and confusing. If you want to take a look at some of the examples that follow, go ahead and you can try them, and I'll see you in class.